Bam, Mr. True. In this video, we're going to start talking about partial fraction decomposition. That means basically we're just going to reverse the addition of fractions. So I've got two examples here where I've got a constant over a linear denominator, degree of 1, plus another constant over another denominator which is linear, x minus 3. I'm showing the steps for finding common denominators because these two denominators have no common factors. So we find those common denominators, we simplify the numerator and denominator, and finally write our answer as 7x minus 1 over x squared minus x minus 6. I've got another example here where I've got 3 over x plus 1, or excuse me, x plus 2, which is a linear expression, plus x minus 4 over x squared plus 1, a quadratic denominator. Now, in this example, and actually this one as well, the degree of the numerator is less than the degree of the denominator. This is a constant or has a degree of 0. This has a degree of 1. In both of these fractions we're about to add. We have a degree of 0 and 1 and a degree of 1 and 2. So for both of these examples, the numerators have a degree that is less than the denominator. And you go through the work of finding a common denominator, simplify those numerators and denominators, and have 4x squared minus 2x minus 5 over x cubed plus 2x squared plus x plus 2. Well, I'm just reminding you, and I'm not going to walk through these because we're not actually teaching how to add algebraic fractions. In this video, we're going to be teaching how to break them apart, how to reverse this addition process. So we're starting from the right-hand side of these examples, and by the end of the video, hopefully being able to go back and find the original fractions that came up with these final two, or come up with a couple of fractions that could come up with these actual fractions here. So, partial fraction decomposition can be written for rational expressions of the form p of x over q of x, where p and q have no common factors, and the highest power in the numerator, in this example it's 1, is less than the highest power in the denominator. So here we have a final answer with a degree of 1 and a degree of 2. So we should be able to reverse this addition process. Same thing here, we have a degree of 2 and a degree of 3. Now there's 4 cases of this partial fraction decomposition where you handle them differently. So we're going to be a bit of a long video. If it gets to be too long, this will be a 2-part video. So, if I finish with example 2, case 1 and case 2 is going to be about when the denominator is linear, or has linear factors, and case 3 and case 4 are going to be when our denominators have some prime quadratic expressions in the denominator. So, if I finish with case 2, there's a part 2, and if I get to all 4 cases, this is a 1-part video, and it will be rather lengthy. So, let's see the next screen. So, through these 4 examples, you're going to see me do these 6 steps. We're going to set up the partial fraction decomposition with unknown constants of a, b, c, however many you need, in the numerators of the decomposed fractions. Then, so I'm going to have an equation set up, and I'm going to multiply both sides by the lowest common denominator. I'm going to have a bunch of fractions set up, so I'm going to look at all those denominators, find the LCM, and then multiply that to both sides of the equation. I will then simplify both sides of the equation, most of the work's going to be on the right, and write the powers, the exponents, in descending order. Then I might have to do a little bit of factoring as well, and I'm going to set the coefficients of like powers of x and the constants. I'm going to solve the remaining linear system of equations for a, b, c, however many I have. And if I do have 3 variables, we're going to have to go back and remember how to solve systems of equations where there's 3 equations and 3 unknowns. That's why I said this video might be kind of long and probably going to be in 2 parts. And then we're going to substitute the values of a, b, c, and etc. back into the equation that we set up in step 1, and in the end, hopefully, we'll have taken a somewhat complex algebraic fraction and broke it apart to find a couple of decomposed fractions of that original problem that we started off with. So let's get to what case 1 is and start our first example. Bam! In case 1, it says, well, we're going to decompose p of x over q of x, where q has only distinct linear factors. So we have p of x over, and we have q of x already in factored form, where it's a sub 1 x plus b sub 1 times a sub 2 x plus b sub 2 dot 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 times a sub n times x plus b sub n. And this just means that we have q of x factored as much as possible. And again, every factor is a unique linear factor. That means a degree of 1. Okay, well this is supposed to be broken up into a sub 1 over, well, capital A sub 1 over a sub 1 times x sub 1 plus b sub 1, that doesn't need to be there, excuse me, plus a sub 2 over a sub 2 x plus b sub 2 dot 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 until plus a sub n over a sub n times x plus b sub n. So all this really means is that this is just q in full factored form, and we've got a different constant, you know, an a sub 1, a sub 2, dot dot dot, a sub n. We're putting a constant over each individual linear factor of q of x. Now, remember, we can't do this process unless the numerator has a degree that is less than the denominator. Also, these are all have degrees of 1. There's the exponents of 1 on the x. So if the numerator is to be a degree less than the, did I just say that right? The degree of the numerator is to be 1 less than the degree of the denominator. So if that's the case, and all of these denominators have degrees of 1, again, that means that the numerators for this particular case must be constants. As I noted in these steps, that a, b, c, and so on do represent constants. Now, the example I'm going to walk through is x plus 5 over x squared minus 6x minus 16. Now, you might be noticing that this is a quadratic and not a linear expression, but it's not necessarily the only, it's not in factored form. If this does factor, then I will have, hopefully, a couple of distinct linear factors. And indeed, this denominator will factor, let's see, factors of the first term go in the first two blanks, so x and x. My last term is negative, so the two signs in my factored version of this quadratic has to have different signs, so 1 plus and 1 minus. And I can just simply look at this constant because my leading coefficient is 1 and go, what factors of 16 subtract to be negative 6? Well, I've got 1 and 16, but that subtracts to be 15. I got 4 and 4, but they subtract to be 0. I have 8 and 2. So if I have a positive 2 and a negative 8, this is the factored form of this expression. So what we're going to do is break this down where we have x plus 5 over x plus 2 times x minus 8. And now I have an expression whose top degree is 1, whose denominator's degree is equal to 2. The denominator was able to be factored into unique or distinct linear factors, and I will not be able to finish, I'm afraid, this problem in the space allotted. So we're going to go ahead and erase this board and give you this problem all nicely spaced out and hopefully very readable, and help you understand what's going on with case number 1. So I got set up example number 1 over here on the blackboard. I like it a little bit better, like writing on it better. We have our expression. We have our expression with the denominator factored with all of our unique linear factors. And then the next step was to write this in a decomposed fashion. In other words, we're going to put, we're going to rewrite this so there's an unknown constant over each unique linear factor. So we're going to have a sub 1 over x minus 8 plus a sub 2 over x plus 2. Now, a couple things to point out. Again, our numerators have to have a degree that's less than the denominator. It is the case in the original problem, degree of 1 and degree of 2. And it is with our decomposed factors as well, or fractions, where these are constants which have a degree of 0, and again, are unique linear denominators which have a degree of 1. Now, I know the formula I just wrote for you said a sub 1, a sub 2, a sub 3, but I'm going to say these, a's and whatever, a sub 1, a sub 2 is a lot, and that's just, I don't like to say, it's just difficult to say over and over and over again. So when you use different subscripts, that is for the purpose of, possibly or actually, yes, having, unique constant values. So just to make it easier to verbalize, I'm going to put a b up here. We're going to multiply both sides of this equation that we have now by the LCM, the lowest common multiple, or a denominator. And that's easy to do since the denominators are already in factored form and all of the factors are indeed unique or distinct. So we're going to multiply this equation through by x minus 8 times x plus 2. So we're going to, and I'm just saving space, I'm not writing this on both sides, but I'll show the lines where I'm connecting this, this multiplication through every single factor, or term, excuse me, of this equation. I'm going to multiply both sides by x minus 8 times x plus 2. So on the left-hand side, all that's going to cancel out, leaving us with x plus 5. Then in the first term, the x minus 8s are going to cancel out, leaving me with a times x plus 2. And in the last term, the x plus 2's are going to cancel out, leaving me with b times x minus 8. Okay, we need to simplify this and ultimately be able to get it organized enough to set up a little system of equations to find out what a and b are. So that means that we're going to have to get rid of parentheses. So we have x plus 5 equals ax plus 2a plus bx minus 8b. Organize the terms so that all the x's are together and get those, if, we are talking about the x's now. If we have x's with degrees of 2, degrees of 1, and constants, get those in decreasing order. So we're going to get x plus 5 equals ax plus bx plus 2a minus 8b. Now, I need to get it written so that I can match up the coefficients. So anytime you have terms with matching factors in them, those need to get factored out. So now we got x minus 5, or plus 5, excuse me, equals, I'm going to take this x out of these first two terms and get a plus b, factor out the x, so it's times x plus, and I'm just going to use these parentheses here to group up the constants and really point them out to you, 2a minus 8b. Now we're ready to match up the coefficients for x squares if we have them, match up the coefficients of x, and then finally the constants. So, and I want to erase this so I can have a bit more room to write, make sure I don't run out of room, and set up this little system. Now we've got the coefficient of this x, which is a plus b, equals the coefficient of x on the left-hand side, which is 1, and our constants of 2a minus 8b, that's equal to our constant of 5. Okay, so you have a small linear system of equations. That's why our book started this chapter off with solving or reminding you how to solve two variable, two equation linear systems, and then we moved on to 3 unknowns and 3 equation linear systems because of this section coming up. So we already have a positive b and a negative b. So let's take the first equation and multiply that by 8 to get the opposites we need in front of those b, that variable of b. So we get 8a plus 8b, and then equals 8. We have we're going to leave the second equation alone because we already have the opposite we need of negative 8b. And now we're going to add those equations, which is going to go ahead and get rid of one of our variables, b, and we have 10a equals 8 plus 5, which is 13, and then a is equal to 13 over 10. Let me just check my work here, and I made a mistake somewhere. Where was that? My notes say I made a mistake. So let's take a pause and find out if my mistake is in my notes or on the chalkboard. Okay, so check my work, check my notes that I'm trying to use to make sure I don't make any mistakes, and I didn't, except I flip-flopped my labels in my notes. So, as far as we got up here, this is good. Lighting's different now because the workday's done. It's not 6 o'clock in the morning anymore. So I might even be a little bit more awake for the rest of this video. Our A value is 13 over 10. So we need to take this, plug it back into one of the original problems. This is clearly, or one of my two original equations of my linear system here, and this is clearly the simpler one. So I'm going to take A, plug it back into my first equation, and we get A, which is 13 over 10, plus B equals 1. We're going to subtract both sides by 13 over 10, and get B is equal to 1 over 1 minus 13 over 10. Now we need common denominators, right, to be able to add or subtract fractions. So we're going to multiply this by the top and bottom by 10, and we get 10 minus 13 is negative 3 over 10. So we have our constants of negative 3 over 10 for B, and we've got A, which is 13 over 10. So we need to come back here and actually write our final answer. Now, our partially, partially decomposition of fractions, we have A over x minus 8 and B over x plus 2. So we're going to come over here and say that we've got A, which is 13 over 10, times, actually since we have some fractional answers here, let's take this A over x minus 8 plus B over x plus 2. I think if I write the final answer, some of you are going to ask me, like, how did that happen? Before I plug in A and B, my fractional answers, let's remember that when you multiply fractions, you go straight across. So I can take this and write it as A over 1, or just A, times 1 over x minus 8, and then we'll have the same thing, pull the B out front, and have it as 1 over x plus 2. So when I have this fractional answer of 13 over 10, and that goes in for A, it's 13 over 10 times 1 over x minus 8. And B is negative 3 over 10. And so our final answer is going to be, if you need to see this, let's see here, 13 over x minus 8 minus, because this is a negative 3, minus 3 over, forgot the 10. Minus 3 over 10 times x plus 2. So bam! That's the first example that we have, or case 1, when our factors are unique linear factors. Our denominators are unique linear factors. Now in that first example, or case number 1, for partial fraction decomposition, I kept stressing that the denominator was, only had unique linear factors. That's because there's another, case or another scenario. What if, when you have p of x over q of x, what if q of x, the denominator, has repeated linear factors? Well, we have p of x, and then that's over ax plus b to the n. Now, this is only how you handle that one factor that has a repetition to it, or a degree that's bigger than 1. That's going to be equal to your constant over ax plus b plus a second constant, a sub 2, over the same factor that has the exponent, ax plus b, and now you raise it to the second power. Now, if this factor had a power of 3 on it, well, then it's plus a sub 3, or another constant, over the same factor in terms of, what's there, ax plus b, and then you let that exponent go up to 3. So you don't write the same factor over and over and over again without changing anything. In the first decomposition fraction, it's just that linear factor. And then in the second fraction, you put an exponent of 2 on it. In the second fraction, you put an exponent of 3 on it. And on and on and on until you reach, whatever that power is that's on that linear factor. So let's see what that looks like as an example. Okay, case number 2, example number 2. We got 3x plus 4 over x cubed minus 6x squared plus 9x. And we want to find the partial fraction decomposition. Pull this fraction apart. Well, right now, this doesn't fit any of the cases I've talked about, which is where the denominator has linear factors. So this must be factorable in the denominator, otherwise we have a problem. So we're going to do 3x plus 4. All these terms, whenever you do factoring, the first thing you should look for is there anything I can factor out of all of the terms? Well, they all have an x, so we're going to pull that x out. X cubed divided by x is x squared. Negative 6x squared divided by x is negative 6x. And then 9x divided by x is 9. Okay, so now I have a linear factor and I have a quadratic factor, but we haven't talked about quadratic factors yet, so this must be factorable again. So we're going to take 3x plus 4 and x. And this trinomial has a leading coefficient of 1, so it shouldn't be too terribly bad to factor. Factors of the first term go in the first 2 blanks, and then factors of the last term go in the last 2 blanks. So my last sign is positive, and my middle sign is negative. So I'm going to have 2 negatives in my 2 factors. And what factors of 9 add to be 6, or negative 6? Well, they both need to be negative 3. So what we have is, we basically just have x times x minus 3 times x minus 3. Well, I was about to erase this, but case 1 was for when each factor of the denominator was a unique linear factor. We do not have a unique or distinct linear factors here. We have x minus 3 showing up twice. So that's, of course, x minus 3 squared, and that's why this is the example we're doing. So what we're supposed to do is, sort of decompose this, expand this out, and we're going to have, let's see, a constant over the first x here. Yes? Yes. Okay. And then plus, now I know the formula I showed you was a1, a sub 2, a sub 3, those different subscripts indicating different constants, but that's hard to say over and over again, so I'm going to just put b over, now what I said was the denominator was ax plus b to the n, and the first denominator of this linear factor that's, that's not unique or that repeats is simply write down that factor. So it's going to be x minus 3, and then that's to the first power, but I'll write it, but it's not going to do anything because raising the number by 1 doesn't change that value. And then plus another constant over that same linear factor squared. And this is probably where the subscripts are nice, because when I wrote, let's see here, for the repeated factor that would have been, well, that'd actually be kind of confusing, wouldn't it? If I said a sub 1, a sub 2, see, but that case that I was talking about only applied to the repeating linear factor, and x doesn't repeat. So really, me personally, I think just having the separate letters is better. So that repeated linear factor, whatever that power is, you started off at 1 and you count up by 1 until you get to that power. So we're done because it was a power of 2. We're going to now multiply this equation by the lowest common multiple, or if you want to call it the lowest common denominator, as if we're going to attempt to add up all these fractions, but we're actually trying to just simply get rid of the fractions. So we're going to multiply by something that cancels out all these denominators, which means we're going to multiply by x times x minus 3 squared. Now when we do that, and I can see already that I'm certainly going to have to pause this video and clean up the board once we're full here pretty soon. So the x times x minus 3 squared and this x times x minus 3 squared, they're going to cancel out. So we have 3x minus 4 on the left. And then now we've got, let's see, x times x minus 3 squared times x. Those x's are going to cancel out, giving us a times x minus 3 squared. And then when we get to the second term, or the third term if you will, but the second term on the right, the x minus 3 will cancel out with one of these x minus 3's, and we get b. Let's see, this is going to cancel out with one of these, so we're going to be left with x times x minus 3, because one of those is canceling with one of these two. And then finally for the last term, x minus 3 squared, x minus 3 squared, that's just going to leave us with the x. Okay, now like the first example, we're going to have to clean this up, get all the like degrees together and in descending order. So we have 3x minus 4 equals a. Please write this twice and actually distribute the x minus 3 times x minus 3, because it is supposed to be x squared minus 6x plus 9. You know, a lot of students will incorrectly write this as x squared minus 9 and forget the middle term. Plus, let's see, well, let's say plus b times x squared minus 3x. I don't know why I didn't just put the b through there as well. Plus cx. And this is equal to 3x minus 4 equals ax squared minus 6ax plus 9a plus bx squared minus 3bx plus cx. Now, I have to rewrite this, but you know what? I don't want to move over here and then just sort of cloud up my entire chalkboard. So I'm going to reorganize these terms where my x squared terms are first, all my x terms are next, and then my constants. We'll clean that up because I'm going to need some extra room here to solve the system of equations that are coming up and get our final answer. So here we go. I put the x squared terms together, all the three terms with x's and the constant at the end. Now before we go and try to make a system of equations out of this, I need to factor out these x's. So we're going to have 3x plus 4. These two terms both have an x squared in them, so I'm going to factor that out and get a plus b times x squared. We've got these three terms with x's, so I'm going to take that out and write plus. I'm doing a plus there in the middle so I don't have to deal with these signs and just keep them negative 6a minus 3b plus c, and then just pulling the x out. Then we have the constant of 9a. Now we have to now write a system of equations. Well, I have to match the x squared coefficient with the x squared that's on the left side, but there is none. So that means that we have a plus b equals to 0, because there is no constant on the left-hand side, or no squared terms. Then we're going to match up the coefficient of the single degree term, or x, with the coefficient over here, which is 3. So we have negative 6a minus 3b plus c equals 3. And then finally, the constants, let's see, I got yellow, green, how about orange? We're going to match up that constant of 4 with this constant of 9a. So 9a equals 4. Now, I made up these problems, because I don't want to take just problems out of the textbook. I'm, trying to make YouTube videos out of this, and I don't want to make copyright issues. So, I got fractions to deal with, so hopefully you're okay with that. We're going to pull this one out here, and we have 9a is equal to 4, and that means that a is equal to 4 over 9. Okay, so now we're going to take this 4 over 9 and plug it into the first equation, and we have, doing some back substitution if you will. So we have from here, let's highlight that, I don't know, let's do that in green or something. So we're going to have a, which is 4 over 9, plus b equals 0. So I'm going to subtract both sides by 4/9, and that didn't take very much work. b is equal to negative 4 over 9. And then finally, with our last line, oh, hope no one ever thinks I'm doing this color coding to match these equations. That probably was maybe not a great idea there. These colors do not relate to those. Okay? Got it. So we have, let's see, -6 and A, which is 4 nights, -3 times B, which is -4 nights. And then we have plus C equals 3. And I got some work to do. So we're going to, well, let's see, we got, well, okay, the 6/9 reduces down to 2/3, right? So we can cross this out. You know what, never mind, I don't like that. Let's just do this. -24/9, -3 times -4 is positive, so we have plus 12/9, plus C equals 3. Okay, this is reducible. I mean, you know, these are reducible. I'm just going to leave it the way it is. We got 24 minus -24 plus 12 is -12/9 plus C equals 3. We're going to go ahead and add 12/9 to both sides. But we need a common denominator, right? That's 3/1. So we're going to make that, we're going to multiply that on the top and bottom by 9. And we get C is equal to 27/9 plus 12/9, which is equal to 27, 37, 39/9. And that reduces, these both have factors of 3, so that reduces to 13/3 for C. So we have our constant of C. We have our constant of B, we have our constant of A. Let me just make sure these are all correct. Yes, they are. So we get A over X. So we have A, which is 4 nights, so we have, this is equal to 4/9X plus B, which is -4 nights, so plus or minus 4/9 times X minus 3 plus C, which is 13/3 times X minus 3 squared. So, bam! Example 2 number done. Example 2 is done. Okay, this video's run fairly long, so that's your 2 cases of how to deal with denominators that have linear factors. Part 2 of this video will be when your denominators have quadratics.